On the exam, what do we know is on the exam?
Reactions.
Right, reactions. We also know he's going to have chapter 5 stuff. We've seen that so many times for so long that hopefully we're all pretty rock star-esque with it. But we'll do a quick flash with that. Chapter 6, which specific stuff that he reviewed that is covered in chapter 6 would be enthalpy and entropy. He didn't really Gibbs energy. He didn't really touch on the Gibbs free energy. Just our other two friends, enthalpy, which measures heat exchange, and entropy, which is our what are we going to call this? Disorder or chaos. So a positive delta H is endothermic. Endo. A negative delta H is exothermic. Entropy is not quite as easily summed up. But in general for entropy, based on the examples we've seen, when we have a decrease, when we decrease order, or for that matter, increase disorder / chaos. I like to think of entropy as like a weird, crazy chaos thing. Wow, makes everything chaotic and disordered. When we increase our disorder or decrease our order, we have a positive change in entropy. When things get crazier. And so how we are going to usually see that in a reaction if, let's say, we have two reactants coming together. So we have our trans double bond. Make it this guy. It's not trans. Our E double bond. Sorry, that's Z. Reacting with HCl. This gives us, according to those on the more substituted, gives us this product. Here we would have the opposite. We have increased order. We've taken two molecules and added them together to make one. So we're building things. We're making things more complicated. We're increasing order in this reaction. So this reaction would have a negative delta S. A reaction with a positive delta S. Can I come up with one of those? That's organic chemistry right off the bat. Yeah. If we have this dude, tree with a little bit of, no, we're going to do this acid catalyzed. We're going to treat this with a wee bit of acid and water to generate the double bond into H2O. Here we've taken one molecule and broken it apart into two different molecules. Here we have a increase in disorder, a positive delta S here, because we broke stuff up. We made things more disordered. Any questions on that? Pretty straightforward for delta S problems. So there's going to be one in the exam. Probably will just come down to count how many molecules there are on either side of your reaction arrow. Entropy, though, is way more exciting than that, I just have to say. So, don't think it's really lame, because it's way cooler than enthalpy, that's for sure. Oops. So that was our general stuff from Chapter 6. And Chapter 6 also covers all of our conventions for mechanisms, and really covers how we discuss mechanisms. I think it also covers...
Do we have to know the specifics regarding mechanisms, or just let me know how to put them together?
you should know how they go together. The book covers things completely different than Dr. Guy. So I kind of like the way the book discusses it. And if you're using your book as a reference, it's also nice to understand the language that they're going to use and the general ideas, the way they discuss things. So if you haven't read it, I'd read it again, or I'd read it. And if you have read it, I'd read it again. Maybe if you've already read it, just skim through it. But it's good to just see the material a few times. So then we skip to Chapter 7. Chapter 8, we only covered 8.1 through 8.5. None of the reactions in Chapter 8 were discussed. So this is just the structure, naming of alkenes and stability. I think that's all we've gotten there. We'll talk about that. And then we hit pretty hard on Chapter 9. And then there's like, in those last two lectures, there's random smatterings of other chapters throughout. Grignard reagents and stuff. You guys all know about Grignards, of course, right?
Sure.
Yeah, that's the answer I wanted. So, before I do all sorts of spiel and talking, does anybody have specific stuff they'd like to have reviewed? Yes.
So can you do like the hydroboration reaction that's on our wheel thing?
Mm-hmm.
Like just so that we have an idea of like how the mechanism works for it.
Okay. The hydroboration
reaction.
Yeah. We're gonna remember how that goes.
You want the wheel?
Well, we have boron. It's going to act as a, I don't remember what substituents we put on here, but boron is like pretty much always a rad electrophile. And we've got a double bond, and we're going to react with that. So that'll behave as our nucleophile. So we'll tack this, form some stable intermediate. Oh yeah, and then we also throw in base, and so if this is substituted, our base will attack at the less substituted position because it's less hindered, of course. Of course. But what is the second reagent we add to eliminate the boron? Do we need sodium borohydride?
So this one, on the wheel it shows, it's this one.
The peroxide is in our second step. Some sort of radical crap? Alright, I'm going to double peek at that mechanism. But that, since our first step is just introducing, it's a two-step reaction. First step is, what was that, just BH3?
Yeah.
BH3 THF, coordinated with THF. So anytime we have boron species in there, boron's really rad because normally a boron molecule is just something like this. It does not have a complete octet. And it's pretty happy without a complete octet, but it would also really like to share electrons. And because of that, it's an awesome electrophile, or Lewis base. I'm sorry, not Lewis base, it's a Lewis acid. Said that wrong, because Lewis acids and electrophiles go together. It likes to accept electrons. And so that's how I knew how to do this first step. So then our second step is we have some NaOH in the mix. What is it?
Yeah.
It was peroxides and
NaOH.
yeah, peroxides and NaOH. So NaOH should probably behave as a nucleophile, I would assume, because this gives us an anti-Markovnikov addition. So our product for this should be. You just get out of here. You guys get out of here. I want to make this less weird. Our product should be this guy, the anti-Markovnikov. We're adding our OH to the less substituted position. So this is an anti-Markovnikov. addition. And that's as opposed to the other additions for OH we learned, either the acid-catalyzed hydration or the hydroboration. I'm sorry, this is the hydroboration. The oxymercuration, demercuration. Yes.
So will we have to like show like that the B comes in the leaves, or can we just show like reactant product?
So I am not exactly sure. He didn't go over this mechanism specifically, so I would assume that you do not need to know it.
Feels like you need to know everything on this wheel, so.
Yeah, so I don't know. It's kind of a little confusing at that point. So I would, dude, you got the mechanism here? I wanna know that I'm wrong because I'm pretty sure those peroxides do something pretty important, but I am not sure what they do. Okay, so for that one, let me just really quick do one more thing. I'll check the appendix. Sorry, I'm dirt facing out. Does anybody out there feel like a boss and know this mechanism? Because Jake clearly is incompetent. Hydroboration oxidation for alkenes 485 or 422. That's looking ahead. Yeah, you guys aren't showing us a fun mechanism, are you? Bunch of shh. Oh, okay, there we go. Oh, wow, isn't that fun? So I'm totally off on this mechanism. Let's go over it right quick. That's fun. So we have not what I did, but a sweet almost, is that like metathesis? Yeah, that's a metathesis. Right? So we have this, I don't think you guys maybe expected to know this, but I don't think he's going to throw this on there. So our first step is this real crazy, wait, no, wrong way. You go, electrons go to the boron, and then this guy, this dude pops off like a hydride and goes yonder, which produces H, and we have our H and our BH2 now. Okay. My gosh. Oh, right. Ah, you're such a schmuck. Okay. Yeah, this mechanism is ridiculous. I totally forgot. So after we form that, we have this fun reaction where we, between our second reagent. So our first step is we add the BH3 coordinated dot THF. And our second step, we have peroxides and NaOH. And these two together form a reactive species. The OH minus, or NaOH, which essentially behaves as OH minus, deprotonates our peroxide. The peroxide then attacks the attacks our oy vey, but there's more here. I didn't even draw it all. But there's more. So this reaction happens like 3 times. So we have another BH there and another H, and this one will like find another double bond. This is why I'm pretty sure you guys don't need to know this mechanism.
Okay.
Because this one's pretty intense.
So for like a reaction like this, should we just know how the product looks like?
Yes, for most of the wheel, I would know the reagents. Just know the reagents for all of that wheel. Some of these mechanisms, though, I don't know if you get tested on because they are a little intense. Anyway, this just to be clear, this goes down again, and we repeat this until we don't have any more hydrogens on our boron. We just have 3 of our starting material guy attached to it. Oh, and then there's I don't want to spend our time going over this. You guys, if you want to check it out, the mechanism is on page 425. But I don't think it's super worthwhile for us to go over. The only other thing I would mention about it is, yeah, we get a sin addition, right? But all right, yeah. So we get sin addition, but that doesn't really matter. All right, yeah. It's not worth talking about, I guess. Yeah, I would check that out, but I'm not going to spend time on it. Sorry.
How
Yeah.
much of the wheel should we know?
I mean, I would know all of the. Can I see peep somebody's wheel real quick?
See.
Yeah, I'm just gonna. So I think he went over all of these reactions.
Clearly.
Yeah, he just crammed. Except he didn't mention the.
He didn't mention like 12, I think. Or 12 or... He didn't mention 11.
He didn't get to 10. He did do 11.
He did do 11?
He did do 11. He didn't mention the one bit 10, the potassium permanganate, KMNO4, NaOH, cold.
Should we still know that reaction though?
I
I would like to know what the products would be and stuff.
You might want to.
Okay.
Yeah, I would say so. What a doozy. What a doozy. DMS, dimethyl sulfide. All right, it's not dimethyl sulfoxide. Okay, cool. So, yeah, for the wheel, geez, I would review problems in the chapter, and also just check out the wheel a few times. I'm not a big advocate of flashcards, but this might be one time where they might work. I kind of hate flashcards personally. I just make them and don't use them because I'm lazy. Okay, were there other specific questions you would want?
Yeah, naming and drawing compounds with E and Z.
Yeah, let's talk about that. That sounds good. But that's, all right, so specifically,
I can't believe he's also that in class.
E, Z, draw, / name. Anybody else have other specific questions? I might just start chucking through stuff. Otherwise, other deep yearning? Yes?
Well, it's not like a deep, like, yearning one, but for, like, the thermodynamics, do you think it's something like the quiz where it's, like, table?
Like it was a table and they're like calculating the
Bonds.
value.
Oh, for the delta H changes in entropy?
Yeah,
Yeah, I would expect.
because he didn't really do anything else. But there were, like, ones in the book, it was, like, which one would you expect? Like, I don't know. There were, like, a whole bunch in the book that he didn't talk about. Yeah. He didn't really do chapter 6.
No, he didn't really. He did. He
He
did.
just like skimmed over it and he's like, hey, look in the book and then...
Okay, read this.
Can't read this. I don't feel like teaching this because it's complicated and difficult. Okay, well let's see if we can roll through some stuff, and I'll try and I'll do things by that. Let's real quick just run through chirality and chiral centers, and then we'll actually skip over chapter 6 and jump into alkenes because those are really similar. So we'll all go through chapter 5 and the little bit of chapter 8 that will be on here. And then we can talk all about chapter 6 with reactions and chapter 9. Great. So chiral centers. We get a chiral center when we have 4 unique substituents. I'm just going to write subs on a carbon.
Wait, I have a question.
And a specific, yeah.
How can a molecule have a chiral center but be achiral?
Ah, it's a really good question. All right, so a molecule can only be achiral if it has 2 chiral centers.
Yes.
Yes. Yeah. A molecule can only be achiral if it has two chiral centers. So for four unique substituents on a carbon, that's sp3, we're going to have a chiral center. If there are two chiral centers with two, or really more, or more, chiral centers, actually, before we mention that, I just want to mention, and for a molecule, a chiral molecule, chiral molecules come in pairs. Pairs or enantiomers. So if we have a chiral molecule, then we have another chiral molecule that is its mirror image. We have, say we've got iodine and chlorine, and like CH3, and we'll put a CF3 back there. Boom, we have a simple chiral molecule. Well, this is always going to have a partner that is its mirror image. Definitely the best way to go about drawing an enantiomer is just to draw a mirror image. Okay, great. So here we have a pair of enantiomers, and I just drew a mirror image to get that. So one chiral center, not too bad, pretty easy peasy. If we want to differentiate between our two enantiomers, we're going to designate one R, and one will be S. And so if we're going to get the RS configuration, our first step is to assign priority to the substituents. And so we determine this based on their atomic mass. Based on atomic mass. So if we look at this one, we can say, all right, iodine has the highest atomic mass. This will be our number one priority. Chlorine has the second highest atomic mass. That should be our second priority. And then we have the annoying part. We have two atoms that are the same atomic mass, carbon. What a bunch of jerks. So in that case, we're going to say, all right, what is that atom attached to? Well, this carbon is attached to fluorines. Well, this carbon is attached to hydrogens. Fluorine is heavier than hydrogen, so this carbon beats out this carbon. So we'd say priority number 3 and 4. So now we have to say, all right, is it RS? How do we do that? Well, 2, if lowest priority is in back, which we don't have. It's kind of annoying. In the back, the dashed line. Clockwise, counting around clockwise from our substituents. Clockwise equals what? R, there. And counterclockwise gives us an S configuration. If the lowest priority is in front, we reverse this. So we have our lowest priority in the front. I'm going to go 1, 2, 3. That makes a nice I'm sorry, I don't know what clocks do. That's counterclockwise. That makes a nice counterclockwise motion, which I would normally say gives us S. But since the lowest priority group is in front, we're going to do the reverse. This is going to be our R enantiomer. And so we can do the same process over here. It's kind of boring. And we know since these two are enantiomers, this should have the opposite configuration. This should be our S enantiomer. Yay! So that's the basics of chirality with simple chiral molecules. And so if we have two, then that's when stuff gets fun. When we have two chiral centers, we have fun enantiomers. We also have rad things called diastereomers. 2 plus centers. So we'll have diastereomers, one group. Diastereomer, really these are, I should specify, diastereomer pairs. So these always come as pairs. Just like enantiomers always come as pairs, diastereomers always come as pairs. And so diastereomers and enantiomers where you have the completely opposite configuration. In a diastereomer pair, one chiral center differs in the pair. So we can have a chiral molecule and we have Br in the back now and Cl still up front. One of our chiral centers differs in this pair. Therefore, this is a pair of diastereomers. Yes?
So would the molecule be achiral because there are 2 chiral centers?
Nay. No. So this molecule cannot be achiral. We can only have an achiral molecule when, for starters, we have symmetry through the molecule. So let's look at a pair that can have some achirality to it. To them.
Do they introduce racemates in chapter 9 only?
Forming racemic mixtures. I mean, they mention in chapter 9, and it kind of carries
Which
over.
if like from if a I don't know, I think I'm jumping too ahead, but if a what do you call it? A reaction is stereopacific or site-specific. Like, how do we know that's going to be a site-specific?
Stereospecific.
Like,
Can you give me an example?
I mean, I'll wait till chapter 9 after you go to chapter 9.
Okay, cool.
Because it introduces it there.
So in this molecule, we can see has some symmetry about it. We have the same substituents on either side. And if we have the same substituents in both of our chiral centers, then if these are, an important thing I didn't mention about chiral centers is that they rotate plane polarized light. And I like that fact for discussing achiral molecules that have chiral centers. So just to discuss that for a second, polarized light, whenever we have light, we know that light behaves as a wave and a particle. But normally light has wavelengths, and all of our different wavelengths are like, they're different faces relative to one another. They're all confused and mixed up, all these different planes of light. So there might be one that's oriented this way, one wave that's oriented this way, all different ways. Plane polarized light is light that's emitted, and the wavelengths are only in one plane. So it's nice, orderly light, orderly beams of light. And so when that kind of light hits a solution or a molecule with a chiral center, the chiral center will rotate that plane that the light wavelength is in. So the wavelength is in one plane, it hits our chiral center, and it rotates. When we have an achiral molecule that has chiral centers in it, what we're looking for is something that should not end up rotating light. And so in this molecule, if we have an H in the back, our priority goes 1 for the bromine. This carbon's going to beat out this carbon because it's got heavier stuff on it. So 2 over here, 3. This guy is 1, 2, 3, R. And our other chiral center is 1, 2, 3. You're also R. Let's draw a diastereomer of this one. This molecule is going to be chiral, but we can draw a diastereomer that should be achiral. we have our BR in the back now.
Wait, but that's a meso, so our meso is just achiral?
Yeah, meso is achiral.
So but if it's achiral, does that mean it's a meso then too?
One,
Does that make sense?
yes, I think
Because like if you rotate around the sigma bond, it's just like a mirror
Yeah.
image. So it's exactly the
it's a
same.
mirror image. Yeah,
Right.
yeah. Meso, I don't think you can have a molecule with chiral centers that's achiral and isn't meso. Yeah. So.
So are they
or-
synonymous, or is it just like a square?
Yes, I think they're
like,
synonymous. I believe they're synonymous. Let me just think about that one more second. We had. Yeah, that would still be 2, 3. Yeah, yeah. If they're mirror images, it's going to be meso. It's going to be achiral.
Okay.
But
Yeah.
it's still a diaster.
So yeah, these are a pair of diastereomers because we've changed one chiral center. This one is R, and this center should now be S. So this is a pair of diastereomers. However, this one is achiral, or meso. And that is because when this plane of polarized light, imagine it's just this light that's wavelengthing inside this plane. When it hits it, the first center is going to rotate it one direction, and the second center is going to rotate it the opposite direction. And that's what happens also when we have just a solution that is a mixture of enantiomers. So a mixture of enantiomers, an even mixture, is what we call a racemic mixture. Loop, loop, loop. Yeah, and racemic mixtures, regular mixtures that are not, that don't have just one specific enantiomer, don't rotate any light. We have to have just exclusively one enantiomer to really see this rotation of light.
When you have symmetry in plane, does that mean it's chiral, or is it achiral?
So when we have
Like that right there, the BR, if you cut it right in half, it's going to see the same thing. It's going to be the same thing.
you mean if we cut it in half? Well, there's no, the way this is drawn, there's no plane of symmetry within that molecule.
Wait, what's the definition of achiral, like, for a molecule?
Achiral, just the definition, means not chiral. Like, atypical is non-typical.
Okay.
Yeah, not chiral. So this compound is achiral and it happens to be meso. We can have compounds that are achiral and aren't meso. For example, if I were to draw like this guy, that molecule is just achiral. Let's put another line on that H. That's just an achiral molecule. It's not chiral at all.
Because it doesn't have 4 substituents? attached?
Exactly.
Okay.
Exactly. Because it does not have 4 unique substituents, it is non-chiral, therefore we call it achiral. This molecule does have chiral centers, yet it is still achiral, and that is because it is meso.
So if you had like a meso like chair compound,
Yes.
and he had like a substituent going off of it, and it was like a methyl, for example, if it's like axial or equatorial, is there like, because I think he said like one of them you can split, but the other one you can't, like down the middle, or can you both split them down the middle, or can they not be split at all? Like, you know, if I gave you like a pentagon and I had like methyl on it, he said you can split that.
I think I understand what you're saying. You mean just for drawing the chairs?
Yeah, if you draw a chair and like you have like a 1 like methyl, but like
Like a 1,2 substituent as opposed
just
to a
like
1,3?
you had like a chair, and then you just shoot a methyl off of it, just like one.
Just one.
Yeah, just one. And then like, but you had another one because I think it was like, I don't know, I did this in book and you put another one, but like the methyl was like equatorial instead of axial.
So we have an axial and an equatorial.
No, like 2 separate molecules.
Two
Like,
separate
one,
molecules.
2 chairs, one is axial, one is equatorial.
Oh shoot, what am I doing now? That's ugly, but whatever. So,
And then that one's equatorial, the methyl.
can I just
Are
plug my...
any of those meso or none of those meso? Like, can you split like the methyl?
Yeah, you can chop that methyl.
Is it only equatorial though, or is it equatorial and axial?
So this molecule is, what do we call this, meso?
There was a problem, I swear to God, he did it with me when I went to go see him, but
I don't think we would call this meso, because meso is used for with two chiral centers, unless I'm just derping up my words. I think this would just be an achiral molecule, because it is symmetrical, but only with one chiral center. Meso, you know, right in here. Oh, yeah. No, okay, that would be meso. So a compound that possesses chirality centers, that's plural. That's plural. Yeah, I don't think that would be meso. I think this is just achiral. And this molecule, I think it's easier to understand that it's achiral if we just draw it as the ring with symmetry, or with the chirality in there. And we can see right here, it's really easy to just chop that right in half. I think it's much harder to see that on the chair.
So that is meso.
This would be not meso, because there's only one chiral center.
So it needs help.
So what? Yes, there must be two chiral centers for it to be meso. This would simply be achiral. And that's because, yeah, there is symmetry and it cuts right through our chiral center.
So if there's two chiral centers and it's R and S, then it's definitely meso.
If they are the same. They have to be the same chiral centers, if that makes sense. So we could have BR. This would be a meso compound. However, this would not. So here, top priority, second priority, third priority, 1, 2, 3. So your R, this is top priority, second priority, third priority, 1, 2, 3. This is S. And we can see the symmetry chopping it in half that way. Here we still have the R and S, but we lack symmetry. Since we have unique chiral centers, this is not going to be a meso compound. This one will be meso. Yes?
Well, since we own it, the chair, if you want to convert it to the ring,
Yeah.
is there room for it? What I meant is, if it's equatorial, it's going to be that, I mean, wedge,
The way
dash.
I do this is,
Because the book asked the equatorial, I mean, there was like two equatorial attached, 1 and 2, and then they were like asking what's the relationship, like, and then the solution book converted to the ring. However, I was confused how they come up with the wedge and dash.
the way I do this is, let's just draw a really preposterous chair for a second. We'll put a tootload of substituents on it. We'll like a BR, and we'll put like a CL, and we'll put like an F, and over here we'll have like a deuterium, because that's fun. We'll put a tritium on the same atom, make it special. Up front here, let's put like, I don't know, another fluorine. And we'll put a bromine on that too. And you're gonna get like CH3. All right, that's enough stuff, I think. So if I want to make this into a nice flat hexane, cyclohexane hexagon drawing, what I'm going to do is I'm going to just put some artificial numbers on it. They're not the proper numbering for this molecule, but they're going to help me do it, this process. So I'm just going to arbitrarily number 1, 2, 3, 4, 5, and 6. Then I'm going to transfer my numbers onto here. 1, 2, 3, 4, 5, and 6. And so now I'm going to look at this structure, and I can see that on every carbon, there are 2 substituents. Some of them aren't drawn in. But in every pair of substituents, one is kind of higher up relative to the other. So here our bromine is higher than our chlorine. On this one, carbon number 2, I didn't do any of these. Let's give you another substituent. Let's put like an iodine there. Here, our iodine is higher up than our CH3. In some of these other ones where I didn't draw in all the substituents, this fluorine is higher up than this axial hydrogen that I didn't draw in. So for every substituent that is higher up in its pair, I'm going to give that a wedged line and say that's above the ring. because it's up, higher up, closer towards me as I draw it. So on this first one, iodine is in the higher up position relative to the CH3. So I'll put a wedge for iodine and a dash for CH3. Moving on to carbon number 2. The fluorine is in the axial position pointing up. And also just for drawing substituents on your chairs, if I could draw a good chair, it might help me talk about this. Or an okay chair. If you're confused about how to draw your substituents, what I do is I figure out how to draw on the axial substituents first. And I look at each carbon and I say, all right, on this carbon, the two lines that go down to make the little point that it is, they kind of make an arrow pointing down. So I'm going to draw my axial carbon pointing straight down. For this carbon up here, the two lines going into it point up. So I'll put my axial substituent pointing straight up. And I can do that for all of these. These guys point up. I'm going to make you kind of bold so we know you're in front. This one points down. That one points down. It goes behind there. You point up. Huzzah. That's all the axial substituents. And if we want to put in the equatorial ones, well, they should just kind of be pointing in the same-ish plane as the ring. This one's a little awkward to do. You can kind of make it poking out there or there. Axial or equatorial substituents. And so we can see in each one of these pairs, this one is higher, this one is higher in this pair versus lower. We can make up nice pairs. Anywho, going back to the example, I'll leave that crap up for a second, even though it looks like a nightmare. So on carbon number 2, we have a fluorine in the higher up position, and we have a bromine in the lower position. On carbon number 3, we don't care about hydrogen. Fluorine is here. Actually, it kind of is helpful to know that these lines should point down for the lower one. Fluorine is up, so we'll put a wedged line. For fluorine, we go to carbon number 4. Deuterium is lower than our tritium. So tritium is higher up, gets the wedge. Deuterium gets the dash. 5 has nothing on it. And 6 has a bromine above the chlorine. What a fun molecule. Yeah, so I look at the chair, I look at where the substituents are relative to one another. The ones that are higher up compared to their partner on that carbon get the wedge, or above the ring. The ones that are lower get below the ring, the dashed line. Does that help?
No?
Yeah?
Because I didn't know how to transfer it.
Yeah, it's definitely weird if you don't have a system for it. It can be quite vexing, I think. All right, where were we? We were talking about meso compounds. I feel like, are we good on meso? Does anybody have any lingering thoughts on meso? Yes.
What I don't get is that, doesn't, a meso compound have to be chiral?
So a meso compound has to have chiral centers in it. But since the two chiral centers are identical but opposite, that ends up making it not rotate plane polarized light, because the one does work, the other one does the opposite work. It cancels out. Because when we have enantiomers, one will rotate light one direction, the other rotates light the other direction. So we have two enantiomers, two chiral centers that are enantiomers of one another in the same molecule. As a result, no light gets rotated, so we call them achiral. But you can still think of them as they do have chiral centers. There is chirality within them, but we call them achiral.
So a chiral molecule will have two S's or two R's?
Yes.
Chiral centers?
Yes.
Okay.
Yes. If they are the same chiral centers.
Yeah.
In that case, they're the same. They're not the same. But they are. They're not mirror images, I guess. So I guess they are the same. It's confusing, a little. Look for the mirror images. Yeah. Any other questions on Chapter 5 chirality stuff? just remember also the rule, if you want to figure out how many chiral centers there are, or how many possible not diastereomers there are. Stereoisomers, thank you. Thank you guys. Just brain farting out. So if we have a molecule that has like a bajillion chiral centers, and we want to figure out how many different configurations of chiral centers there are, how many different stereoisomers there are, we're going to use the 2 to the n plus 1? No, just 2 to the n. Just 2 to the n, yeah. So if there's only one chiral center, then we have enantiomers. There are 2 possible stereoisomers. This guy and its mirror image, this guy. Just pretend there's fun substituents on there. If we have another, then diastereomers, we have 4. If we have 2 chiral centers, there's 4 possible stereoisomers, blah, 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 blah. It's possible there will be a throwaway question on that. Or one that's disproportionately weighted. So keeping going with this whole priority thing, and this wonderful Koenig-Gold Prelog paper, we can use this system for naming and describing double bonded molecules. Let's make you a double bonded molecule. So this is getting into chapter 8. So double bonded molecules, we can have them show up in a few different forms. We can have tetrasubstituted, where we have 4 carbon-based substituents coming off of our double bond carbons. So these guys have 1, 2, 3, 4 substituents that are carbon-based total. We could have a tri-substituted. We only have 3 substituents.
So would that one also be tri?
This would also be a tri-substituted, correct. Right. And then if we get into the di-substituted, there's a few different ways we can build a di-substituted molecule. We could either have a trans di-substituted. So if we only have 2 substituents, naming is easy. We can have trans. We can have cis. Or we can have both of our attachments are substituents on the same carbon, which we don't really have a fun name for. I think there's a fun name for you. And then lastly, we can have a monosubstituted alkene that just has 1 carbon bond. And then we just also have our simplest alkene, which is ethene, which is just 2 carbons who are double bonded, and therefore collective hydrogens. When we have tetrasubstituted and tri-substituted, we have to let, if we're writing the name for this, we have to let the reader know what order these guys are in. Because this molecule is distinctly different from this molecule. Those would be stereoisomers. They are going to have the same, not stereoisomers, stereoisomers? Conformational isomers, yeah. They have the same molecules, but they're put together. No, you're not technically conformational isomers, you're stereoisomers.
Constitutional isomers.
Constitutional isomers? Are they constitutional, the constituents? Huh?
When they're on different places in here.
Different faces of the...
Places like when you move, you just moved it, so it's like it makes it a constitutional.
It's a constitutional isomer, yeah. Okay. Not quite sure about that. But either way, these are unique molecules, huh?
I got it right on the.
You good? So that's, all right, so they're constitutional isomers. All right. Constitutional. Right, because our attachment of atoms is different. Derp. We put our things together differently. So these are unique molecules. We have to be able to tell a reader which one we have. And for that, we have this really fun system, the E and Z system. While I have this up here, though, let's really quickly talk about stability of alkenes. So I've drawn them in a specific way because it's helpful. We have an increasing stability as we add more substituents into our alkene. So the more substituted our alkene is, the more stable. That's pretty much been the rule for every funky group we've looked at thus far. For carbocations, the more substituted, the more stable. We briefly talked about, Dr. Face Guy mentioned radicals. With those, the more substituted, the more stable. So, yeah, it's been the trend. If you remember that, good to go. If you haven't, the best time ever. So E and Z, differentiating E and Z, how do we do that? Well, we're going to use that same system for assigning priority that we used for chirality. So we look and we say, all right, what substituent is heaviest? Let's change this example. Let's make you a fluorine. We say what we look at one of the carbons. So let's look at this one, and we look at substituents. We don't really care about this other carbon. We want to know about the substituents, the other stuff, the non-double bond stuff. And so up here there's a hydrogen. So we compare a C to an H. Carbon is the heavier atom. It is higher priority. Dr. Dude uses an H. We'll just do that. I've been using a 1 and a 2. No, I'm going to stick with my shiz. So I'm going to give you top priority, number 1, your lower priority, number 2. We look at our second carbon that's participating in the double bond, and we look at its substituents and say which atom that's initially attached is heavier. We have fluorine and carbon. Fluorine is heavier, so it gets top priority, number 1. And carbon is lower priority, so it's number 2. So when we have our substituents on the opposite side of the molecule, this is an E configuration. And they are on the opposite. Or like German for apart, which I don't remember. Does anybody speak German? Apart? German? I think it was like Engeigen or something. I don't recall. E is apart or opposite. If we had a fun Z molecule, let's put in like that and we'll put in, let's make you a CF3, and you'll be like I. So we have this molecule. We want to assign priority to this. All right, let's start over here. This carbon is attached to a carbon and an iodine. Iodine is our heavier atom, so iodine gets top priority, number 1. Carbon gets number 2. And on the other side, we have carbon, and it's bound to carbon up here and carbon down there. So we have to explore these a little further. Down below, we have a carbon with 1, 2, 3 bonds to carbon. Carbon bonds. Up top, we have a carbon, and this has 2 bonds to carbon and 1 bond to chlorine. So which takes priority, top or bottom? Anybody? Top, right, because it has the heavier atom attached to it. So because this carbon has a heavier substituent on it, it wins. So you're number 1. They are on the same side, so this is Z, or like Ziffenzeifen, or some fun-sounding German word, for together. And the way I always remember this is because of the epic fail I made, where I looked at these and I was like, Z. I didn't draw Z's with the lines in the past. And I drew my Z and I was like, look, the lines are on the opposite side. This must be the one where they're opposite. And that's so wrong. That's so wrong. It's totally wrong. It's 100% wrong. And I made that mistake like twice, I think. And I've never made that mistake since. So don't be a dummy and look for easy patterns in the letters. If anything, remember that I'm a dummy and thought Z, they're opposite.
The way I do it is like, I just look like when you make a Z, it's high,
Hi.
It's the same.
It's Z same. I kind of like that. I didn't quite get your.
Yeah, it's like
Charles
Charles
said
is
Z,
the same, and
Yeah,
it's
same.
the S.
Yeah.
He was
Right.
serious too.
Hi.
He was
Hi.
like-
He was all low. Like he calls him hi.
Oh, like how you make your Z?
I had low.
Okay. All right.
Wait,
I like Z same though personally because I like.
Name
Huh?
Can we name them?
Yeah, we can totally name them. Oh, this one's gonna be difficult to name. Or it's gonna be a little different because it has the triple bond in it, the alkyne, and that gets priority. So let's take the alkyne out of here. Let's make that a double bond. That'll be more fun. Okay, cool. So if we're gonna name these, we have to remember that our carbon or a double bond takes priority for naming these. So let me can I jazz one of these up so it's funky. I don't know how to do that real quick.
No, we should just like leave it.
Let's just leave them as they are. I'll do another example. Right, we want to find the longest carbon chain that includes our alkene, and the longest one looks to be 1, 2, 3, 4, 5, 6, all of the freaking carbons in the molecule. Great. So we know that this is going to be hex, 6 carbons, and it gets the ene suffix because we have a double bond in there. So let's figure out the numbering. Get out of here, hydrogen. You're a little confusing. Let's figure out the numbering, and I'm going to make you a little bit lower so I don't have a spacing issue. Hex ene. So we want to number this so that our double bond is closest to our first number, or it should be closest to our starting side. So we won't pick over here because it's a long way to the double bond versus here. So this should be our starting carbon. So we can count 1, 2 instead of 1, 2, 3, 4. So 1, 2, 3, 4, 5, 6. Groovy. So to put a number, so we always have to, we should always number where our double bond is in our ring. So we'll call this 2-hexene because our double bond starts in carbon number 2 and goes into number 3. So we'll always number it the double bond for which carbon it starts in. This is 2-hexene. You can alternatively write this as hex 2-ene, which I personally like more because it puts the 2 right with that ene suffix. That, I don't know, the breakdown for that I find very, very logical. Oh, there's 6 carbons, and at carbon number 2 we have a double bond. Great. Instead of 2-hexene, it's pretty much the same thing. But that's, we have to give a number so the reader knows where in our 6 carbon chain to put the double bond. And then after that, we're just going to go ahead and number our substituents normally. So we've got a fluorine in here. This will be 3 fluoro. And we said earlier that this is E, right?
Yes.
Yes. Yeah, E. So we're going to call this just E, right? Do we have to call you 2E?
In the book, in front of the name, they put parentheses and E.
Yeah.
Yeah.
Yeah. Do you want to put the methyl group?
No, dude, because it's part of our carbon chain.
Oh, yeah. No.
That's carbon number 1. We will also just... No, never mind. Sorry, I was going to say something stupid. Yeah, so this is going to be E. That one's nice and simple. Right, that's why I was getting the numbering mixed up. We have 2 double bonds in this one. So this is a little bit more of a...
Wait, only 3?
Oh, yeah, we have 3. Holy cow. You're a terrible monster. And they're almost the same. All right, so we want to find the longest... let's take one of you out here. Let's just put some other fun stuff on this. Trienes? Yeah, we're not naming trienes right now. Put like a fluorine and a bromine on there. Okay, cool. So we want to come up with the longest chain here that contains we want to have both of our double bonds in it. So even though we could technically make the longest chain by going 1, 2, 3, 4, 5, or something like that, 2, 3, 4, 5, 6, I guess that would be the longest one. We're not going to do that. Oh, I forgot about you. You're a carbon also. Look at that. We want to have all of our double bonds in our chain because they take priority. So we're going to make the longest chain we can using our double bonds. And so that would be what? Yeah, a pentene, right. 5 carbons. 1, 2, 3, 4, 5. So we probably won't number it that way. But it's going to be a pent. It's going to be our prefix here. We're going to use actually penta because this is not going to have a regular -ene suffix. This is going to have a die-ene. Oops. Die-ene suffix. Because there are 2 double bonds, 2 enes up in there. They're ene there. Right? No. No, don't laugh at that. It was bad. So we want to do our numbering on this. Let's get our numbering down for starters. We want to number so that our double bonds get the lowest numbering. So we could either start here, but that's silly because then we'd get to them. If we start here, we're right off the bat in a double bond. Shazam. So we'll start over here with 1, 2, 3, 4, 5. So this is going to be for our numbering. We want to put our numbers for where our double bonds are in right before the root name. So this would be, what would the numbering on this be? 1 and 3, right, because our double bonds start at carbon 1 and at carbon 3. 1, 3 pentadiene. And then we just have to name our substituents on here. Oh, why do I have so many substituents? Why did I do that? So we've got an iodo group. We've got 3 fluoros. And we've got this ugly turd who we have to name.
Do you have a name?
Yes, when we have complicated substituents like this, what we're going to do is we're going to give them complicated names. We're going to name this kind of like it was its own molecule. So, are we done with this? Yeah, we're done with this. Get out here. I'm just going to redraw that substituent real quick. How are we doing on time? Okay, cool.
510.
So I'm going to redraw that substituent. If it were not attached to this molecule, this would just be F and a Br. And I'm going to number it as though the place that it was attached is carbon number 1. So this would be 1, 2, 3. I would call this 1 bromo, 2 fluoro, no hyphen there, 2 fluoro propane. I know words. Okay, cool. So that's the name of this molecule. If this were if this didn't have the bromine and the fluorine on it, it would just be propane, right? And if we were naming it, we would just convert propane to propyl. We would just say, oh yeah, it's a 3-propyl group. We're going to do the same thing with this more complicated name. We're just going to chop off the ending, and we're going to put the whole sucker in parentheses so that we don't get confused, so that we don't think that this bromine is part of our primary chain. We're going to name our offshoot like it was its own chain, keeping in mind that our numbering starts where it's attached to our main molecule chain. So I wrote that real big there, and I just kind of want to write it there again in a second. So this is our 1 bromo, 2 fluoro, propyl group. And so then numbering it, who comes first? I think propyl, you get your root suffix with propyl, so we do the fluoroiodo. So this would be 5, 5, 5, tri-fluoro. So we have 3 of them on that dude.
Forgetting the chlorine, Jim.
Oh, what? There's a chlorine?
Yeah.
No! Oh, I hate everything. That's fine. I can put it out front. It's great. Everything's great. I didn't forget that. I'm dyslexic. That's a terrible excuse, and would actually, no, dyslexia is a real thing, and I shouldn't pretend that I have it. I'm sorry if anyone suffers from dyslexia, that was very insensitive. So this is going to be 2-chloro, 2-chloro, 5-5-5, trifluoro. That thing, because the P becomes, no, I comes out before P.
Does the number go with fluoro, 2-fluoro?
Yes, sorry, I totally forgot that. Bromo,
2-fluoro.
2-fluoro. I'll get it. There's not enough room to write it. Naming! 4-iodo. And then we would write in this long name in parentheses. So we would say 3-1-bromo, blah, 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 blah. 1-bromo, 2-fluoro, propyl, parentheses. Then our 1,3-pentadiene. Oh, what a name. What a mother fudging name. But anyway, the main takeaway of this is
Dr. Hill not going to keep that.
no. I don't think you're going to see any crazy, complicated. But I like to throw those in just so that, just so you guys, yeah, you do never know. And it's good to know how to name complicated substituents. It's not very hard. Well, we can see it's not very hard. You just chop it off and make it its own molecule, and then give it that ol suffix to say that it's not the main thing. Oh, crazy compound! And yeah, for your double bonds, they take priority, and you have to let the reader know where they are in the chain. You let them know the first carbon that is getting the double bond. Cool. So I think and we talked about stability, tri, tetra. Okay, cool. So we're pretty good to talk about reactions. So many.
What do you, like, he gave us a lot, like, in class.
Yeah.
Like, a lot of examples. I mean, it's a lot to study. What do you think he's, like, actually going to give us on the test?
I mean, he's probably pulling most of the questions directly out of the textbook.
You think?
Yeah, I think he said that. Somebody told me he said that to them.
Yeah, he did say like he's going to use a lot of like
It's a
problems based off
imagination,
textbook.
so he's going to put the problems.
Yeah.
Yes, that too. So go through look at your recitation worksheets. Yeah, he loves to just copy and paste those. Yeah, look.
Besides looking at our notes.
Definitely that. Also, you guys, when you're in class, if he seems to get excited about something, like, just put a star next to whatever topic he's talking about.
Kept
'Cause-
stressing problem 9.22. Could we look at that at some point?
Yeah,
I don't know
he's-
if it's a mechanism.
yeah, you definitely, 9.22, he mentioned. Oh, that's like somewhere in the chapter. 9.22.
Right, Mr. Gray, quick question.
Yeah.
How far should I look into the chapter 9? Like half of it?
I think he covered the entirety of chapter 9.
Well, he covered it by he gave us the wheel and said learn it.
Memorize the wheel.
I thought we only went up to like 9 point. We only went up to hello.
Oh my god, my hair.
We're going to do this.
Because there's
Yeah,
a lot of
halohydrin
stuff
formation.
that I didn't hear it in class.
That was, no, he went, I mean, on Wednesday he continued talking about osmo, yeah, he got all this. Yeah, I mean, he mentioned it. That's about all that happened with anything.
He can just say he mentioned the book.
There's a book, you should know everything. Come on,
I mean,
why aren't you guys working in labs yet?
What?
You have the textbook, you should have, like, gotten jobs by now. As organic chemist, yeah. You-
Charles is really complicated, like the splitting of the double and then opening of the ring. Is that true? He like wouldn't even show me.
He showed the mechanism in class, I thought.
He kind of like.
He
Well,
just
I went
broke
to
it
Charles
apart.
yesterday.
Yeah,
and
he
I was
just-
doing it, and he was like, "That's not actually right, but like, if you think about it correctly, it's right." Like where you like flip the oxygens so they're oriented, and then you just smush it together.
It's like a puzzle.
Yeah, that one. But Charles was like, that's not actually like a mechanism, that's just how you
Great.
Oh, how to know how to do these?
Yeah.
Yeah, the way I do these, all right, so yeah. For these, what, we have the two conditions. We've got ozone and DMS for the reductive. And
There's hydrogen peroxide and other one.
yeah, yes, thank you. Ozone and peroxides for the oxidative. What does that oxidative versus reductive mean? I don't know. No, I do. We've got basically we're oxidizing our carbons more, but the way I think about it to keep it real simple is there's going to be more oxygens in our oxidative product. There's more oxidizing. Let's put an oxygen on stuff to be super simplistic about it. So the easy way to do these is, for starters, when you see this, is we're going to chop our double bond in half. So I like to draw a jumbo-sized version of the molecule to make my life a little easier. And I don't actually draw the double bond. I draw it chopped in half because we're going to chop our double bond in half. Our product, we're going to get two carbonyl groups out of this, C double bond O's. So we're going to chop our double bond in half. Where there was a double bond, I'm going to put in an O for each side. So each side gets a carbonyl. And bam, that's our product.
Seriously?
Ta-da! That's it. We did it.
That's
I didn't include the hydrogens in here, but you don't even have to. That's the product. That's it.
Should it open?
Should it be open?
I mean, yeah, you could technically draw it open, but
You don't need
so
to.
yeah, you should. I mean, I guess you should redraw it technically, but they're the same molecule. So this is 6 carbons. This is the same thing, just drawn a little different. But that is the easy peasy way to do these. So let's still look at it with a different substrate. And so this is just the reductive version. Let's just look at another double bond. Put like this guy. We hit it with that ozone and dimethyl sulfide, DMS. That's methyl sulfur with 2 CH3s on it. So same thing, I'm just going to redraw this. Double bond, chopped in half. And I'm going to plunk in some O's. I got 2 products this time. Got this guy plus. Bam.
You don't think he's gonna make us do the mechanism for that?
You didn't really.
Is that difficult if we have to show the mechanism for it?
Charles wouldn't show me it in lab. He's like, oh, no.
Yeah, he's like, I'm not gonna show it to you. Like, we're half done. Okay.
He. So what I can pull up exactly what he showed in class. Let me just grab that off of my machine because I don't recall the exact
Can we
structures.
ask him to use Blackboard? This would be fantastic.
I don't think he knows how.
Yeah, he won't. Don't. No.
Can I
I-
feed?
Kim, the advisor, pre-professional, had
Is that-
him
yeah.
in college and said he
Oh my
does
God,
the
he's
same
ancient.
thing now that he does.
No, his
back
the things he has, the sheets he's using are like,
old.
yeah, they're from a textbook from who knows when.
Some of
Um,
them aren't his though. Like some of them he didn't even write. He took from someone else. Apparently.
where? Okay, so
Why write your own when you
yeah,
can?
all he discussed for this was he just showed some of the key intermediates. So I wouldn't worry too much about the mechanism. All that he, oops, gotta fix my webcam action. Doo-doo.
This up on Blackboard?
Huh?
Are you putting this up on Blackboard?
On Blackboard?
Yeah.
No, like the web.
Yeah.
It's on YouTube's. It's on them YouTube's. I'll try and make it more search friendly. I'll put my name Winegrad like 8,000 times in it or something. Or Winegrad Chemistry.
Email the link out?
I did. I thought so if you guys aren't receiving emails from me, because I also sent out updated.
Yeah, we have Charles.
Okay, so for you folks who don't have me for
You should email
recitation,
to Charles and tell him to email it.
huh? I guess I could
That would be
also.
really
How about
easy.
you just, how about you just give us your information?
Yeah. How about y'all just email me TC727. Well, wait, I don't use my Temple email address. It's jwinegra@thegmails. So send me an email and just like put your, it'll obviously come through your email address. So, and just ask to be attached into my emailing chain for chemistry stuff. I sent out, from his later lecture notes that I typed up. Also, I'll mention this again. If you guys don't know, ChemDraw is a piece of software that you can use that's real fun for doing science stuff. I used it to type up notes. You can use it to draw structures. And once you've done that, it can help you predict names, I think. But it can definitely help you predict NMR structures or IR structures. And generally, it's kind of fun to play around with.
What's that?
ChemDraw?
We didn't
No,
learn
we
that
didn't
yet.
learn MRI or SRI or.
NMR, IR structures? Well, you will. It will come in time. You should have learned about it. They should have mentioned it in the lab.
Yeah, with the IR spectrum.
Oh.
Yeah, IR spectrums and NMR
Is
spectrums.
that like Spartan? Those kind of
Not
programs?
really. Spartan has much more power in that regard. This is mostly just for drawing, but it has some weak computational power. Anyway, you guys can get it for free. Just Google Temple ChemDraw. One of the first links that comes up should be from the College of Science and Technology webpage. You click on that. Huh?
No one tells us.
Charles doesn't tell us this.
No one tells anyone this.
Hill didn't tell us either.
No, I don't think this is normally shared. Information. I guess they don't think you guys need it or something. But it's nice. It's also cool if you want it for your lab reports. Have real crisp structures drawn up.
I got points taken off for that. That might be-
Crisp structures with that ChemDraw.
happened?
Anyway, follow the links.
Jordan paint,
Google
takes
this.
it off.
You'll
I
get
got
taken to a
points
page
taken
where you have to put in, I think, your Temple email, and you'll get some confirmation code for a download. It's pretty easy.
The reaction speeds and stuff.
You did Google.
They want you
Um,
to hand draw, even if you do copy. They want
All right. Let's get focused again. So this was the reductive version of this cleavage. This is still oxidative cleavage, but under reductive conditions. If we do this with the peroxides in place, what's going to happen is any hydrogens that are part of this double bond, they're going to get the crap oxidized out of them. They're going to get pajowed, if you will. That's very scientific talk. So instead of having hydrogen in our product, we're going to replace those with OHs. This is a more oxidized carbon. It's got more oxygens on it. Oxidized. Very easy way to remember those terms. So this is a more oxidized carbon than if we used our gentle conditions to generate these. So these are aldehydes. These are carbonyls or C double bond O's that have one hydrogen and one carbon substituent on them. Cha-cha-cha. These are carboxylic acids. If we have a tetrasubstrate, this is a tri-substituted substrate. If we hit this with the ozone and hydrogen peroxide, it will not mess with any carbon-carbon bonds. So this will still give us this group up here. This is a ketone, a carbonyl that has two carbons attached to it. But down here, this hydrogen is going to get converted into an OH. This carbon is untouched. So when we use these peroxide conditions, we're going to convert any hydrogen that is bound to our double bonded carbons to an OH when we do our cleavage. Cleavage. So there were like two mechanisms. There was one that he was like, no, you should definitely KNOW this one. Which one was that?
Bromine.
It was the bromine.
Bromination, HBr?
Yeah.
Yeah, all right. Let's go over that sucker one more time.
And BR2.
Yeah, VR too.
Yeah, I also like BR2 a lot because it's got that real dope bromonium ion. I love broing out with it. I think there's fun jokes to be made there. So they have very different intermediates. The first one, let's do our HBr addition, or halogenation, simple halogenation. So the mechanism for this. I like to, when I'm doing mechanisms, look at our reactions or reactants and say, all right, are these nucleophiles? Are they electrophiles? But before we actually get into the mechanism, what product is this going to give us? We're going to,
It's going to give us a
Double
bromine.
bond
right, we drop our double bond, we're going to kick that out, and we're going to put the hydrogen,
on the least substitute.
right, hydrogen will be on our less substituted side, so this new fancy hydrogen will be there, and our bromine will be on the more substituted position. And we're going to end up getting this because we have a doped carbocation intermediate. Carbocation intermediate, it's so rad. Actually, the carbocation intermediate kind of sucks for real life purposes. So we start with our alkene and our HBr. Boop, boop, boop. Right. So generally, also, I usually think of acids just as existing as H+, particularly strong acids. But if we want to be really fancy, we will show it as HBr. Instead of just showing our, well, let me backtrack a second. Yeah, I like to think of strong acids as just H+. And because of that, I generally designate them. H+ has positive charge. It wants electrons with its positive charge. It loves electrons. Therefore, it is an electrophile. So I usually consider strong acids to be electrophiles, or at least the hydrogen on them to behave as an electrophile. Looking at our double bond, our alkene, we can think, all right, double bonds, those are nucleophiles. Nucleophiles being compounds that want to get positive charge. Compounds that have excess electrons, either in p orbitals, or as lone pairs, as partial negative charges, but in particular double bonds make pretty nice nucleophiles. So we can say that this is going to be our nucleophile for our first step. And so our nucleophile attacks the electrophile with its electrons. So we're going to draw an arrow showing the flow of these electrons. They come from the nucleophile, who has them. It attacks the electrophile. It attacks this positively charged hydrogen, who normally I would just kind of pretend is an H+. When this hydrogen gets attacked, we're going to have a bond being formed. Pretty much every arrow generates a bond. Either a bond moves or a bond breaks when we have arrows flowing. So here we have a bond breaking. This double bond breaks, and we're going to generate a bond to this hydrogen. And hydrogen only wants to have one bond at a time. So as a result, it breaks its existing bond, and those electrons kick onto bromine, who's like, yeah, dude, totally. I love having negative charge. I'm bromine, I'm very electronegative. Give me the electrons. So this is our first step, and it generates our intermediate species. Intermediate, and this is a carbocation. Can I spell intermediate? Yeah, I can. All right. I was going for like intermediation. Yeah, great. That A is a little crazy. So this is not the substrate we're working with. So we've broken our double bond. If we want to draw this nice, start without your double bond in there and just draw the rest of your molecule. And we're going to attach the double bond to, the hydrogen to our less substituted carbon. It's going to go on the less substituted carbon. This one has one substituent. This one has two. And that's because in the position that the hydrogen is not, the carbon that did not receive the hydrogen forms our carbocation. And our carbocation, I think I mentioned this before when I was talking about alkenes, more substituted, more stable. So our carbocation does not want to be the other potential intermediate we could form would be, let's draw on that hydrogen. Well, the two here.
You have to show the minor product or no?
No. I would not show minor products unless explicitly asked to. So this is our other possible formation. We could put the hydrogen on the more substituted carbon, but this gives us a secondary carbocation. the carbon that holds this positive charge has 2 bonds to carbon substituents, secondary, versus this carbon holding the positive charge, which has 1, 2, 3 bonds to other carbons. So this is a tertiary carbocation and is more stable than this secondary carbocation. We don't really see formation of that species.
We don't have to write that, do we?
No, I would not. I would not write that in for the mechanism. I just wanted to be clear why you
Show.
wouldn't
Okay.
do that.
Jake, how do you know which arrows to use, the reverse arrows or the single?
The single-headed or the half-headed?
Right.
We're pretty much always going to be using the double-headed regular arrows, unless you see peroxides in the mix. No, that's not true. There's like there's a handful of mechanisms that use the half-headed arrows.
And how do you know about the equilibrium? Like, how do you know if they're
When we use, so did you mean these guys?
Yeah.
Or I see. When we have an equilibrium process. Some of those, for your level, I think I would just memorize pretty much every proton transfer, basic proton, like if an O grabs a proton or gives up a proton, oxygen, that's going to be a simple reversible step. This is
Well, chapter 6 talks about it, but it doesn't really
specifically say it.
It's just like saying that it's reversible if this electrophile is like unknown. Nucleophilic attack is weak or something like that.
Yeah, so if we don't have a super amazing nucleophile or super amazing electrophile, this reaction isn't super blammo, very quick and efficient, generally forming a carbocation, for example, I would expect this to be reversible.
Wait, how do you know which one's the nucleophile and which one's the electrophile?
So the nucleophile, great question, is going to nucleophiles. There's a nice list, I think, either in chapter 8 or chapter 6 or 7. The nucleophiles in general have an abundance.
Chapter 6.
Yeah, negative charge. And so we'll find this either as an anion, a molecule with lone pairs, so an anion might, for example, Br minus, or Cn minus. Put our lone pairs on these. It could be a molecule that just has lone pairs but not charge. For example, water sometimes behaves as a nucleophile. It's not a very good one, but sometimes it behaves as one. Ammonia also sometimes behaves as a nucleophile, or other times we will see, sometimes we see ethers, sorry, not ethers, alcohols behaving as nucleophiles.
The book talks about 3 categories, like the presence of double bonds.
Yes, that was what I was getting to next, double bonds.
And then the molecule that has an inductive effect, which is like electronegativity difference. And
Yes.
The third one is lone pair, the presence of lone pair.
Presence of lone pairs. So they also mentioned inductive effects. What I'm trying to think of an example.
Also hydrogen and chlorine.
Really?
Could be hydrochloric acid. Could be that.
Right, but there we still have a lone pair. I'm just trying to think of something that.
So is it the one with the double bond, because it's like the nucleophile?
Yes.
And then the thing that you're being added to is like the
The
electrophile.
electrophile.
Is that how like it generally goes?
Show the BR there.
For the examples we're
What?
looking at now,
Should
yes.
extra
And that's
BR.
because double bonds
Mind
are
if
generally
you-
good
That's what it
nucleophiles.
was.
In most reactions we do, double bonds will behave as nucleophiles. They have an abundance of negative charge there. There's extra electrons between those carbons.
But it's not like noted that it's negative. Like we don't have to put like.
No, there is no negative charge
Like when you
on
add,
it.
like after that reaction, then you like add like plus Br minus and like a little circle. Like, you know,
Yes.
to add. So
Nope.
we don't draw like a negative charge on.
On your...
Yeah, like
No.
we had to do the whole mechanism out ourselves. Okay.
No, because there is no negative charge.
The logic
There.
behind it is sp2. So that's a planar. planar, and then the pi bond sticks up.
Yeah, the reason, so there's,
On the one.
I'm not going to be able to draw it well.
It's nothing new.
Yeah, but where is it? There's a really dope image in the book. I'm not sure what page it's on though.
It's in chapter 6.
It's in chapter 6, really?
Yeah.
Wait, which one?
So there's a really dope drawing illustration where they show the double bonds, or the pi orbitals in a double bond.
I did like.
But I'm not, it's a carbocation. Alright, anyway, I'm going to try and draw the double bond thing really quick. And then continue on with this mechanism. So our double bonds sit in a plane. Carbon and your substituents are out there. Carbon and your substituents are out there. I guess you're all in the plane. They're all in this nice flat plane. And their p orbitals extend above the plane. If we had a carbon, above and below the plane. So there's a p orbital. I'm going to do thick lines for being above. That pops out above this plane that I've drawn on each of these carbons. And one that is below the plane as well. And because this is nice and flat, it's very easy for these to interact with other molecules. There's not a lot of steric hindrance or other atoms or molecules getting in the way. Okay, cool. So that's why double bonds behave as nice nucleophiles. Yeah?
The mechanism part, you know how you added the H?
Yes.
Do you have to?
Because I get confused without it.
Well, I'm just saying, because it's kind of known that there is an H going to be on there, because in the book, the solutions, they didn't put the H's.
This one?
Like, after you add the HBr.
Oh, no, you don't have to.
Okay.
I like to do that personally.
I do too.
Yeah, there's nothing wrong with that.
Okay.
But it definitely helps for just making sure everything's lined up dope. All right, so moving on with this mechanism. Sorry for all the sidetracks. We're looking at our second step now, and we want to figure out what's going to happen. I again like to say, do we have a nucleophile? Do we have a clear nucleophile? Do we have a clear electrophile?
Electrophile.
We definitely, yeah, we have an amazing electrophile here. Our carbocation is a great example of an electrophile. We know carbon likes to have 4 bonds on it. This carbon doesn't. It has a full-blown positive charge. It wants to get electrons to make that 4th bond. It wants to get electrons to complete its octet. It's a really unhappy carbon, and it is dying for electrons. It loves them so much.
So that's an electrophile?
So that's an electrophile. And I said this weird thing earlier, it's going to come off as kind of creepy, but if you can't keep an electrophile and a nucleophile straight, I just remember, all right, pedophiles love children. That is where the suffix phile comes from, to love. Yeah, it's philo, Greek. But that's how I keep it straight. Electrophile, it loves electrons. A nucleophile, that one's a little bit more vague. It loves nucleuses. There's positive charge there. But I remember electrophile, it loves electrons, like pedophiles. Love children.
Why is the HBr then an electrophile?
So the HBr is an electrophile because we have hydrogen hooked up with this bromine. Bromine is very electronegative compared to the hydrogen. And it has an inductive effect. It pulls and it induces
So like
the
he makes us right under it, the
deltas.
Oh, the little partial.
Yes. So you can either use an arrow,
Yeah.
or you can use that's a crappy delta.
Well, you have to do that?
It's good too. You don't have to for your mechanisms.
So technically the whole thing is an electrophile, just like the H is kind of like the electrophile.
Yeah, it's really the H is an electrophile. And honestly, if I were doing this problem, I would just be like, yeah, and there's H plus because HBr dissociates because it's a strong acid.
Right.
Right.
Well, if you have a question, the book 256 to 258 covers the thing.
I've been way too much on the client.
Yeah, it's definitely covered in the book. Beautifully. Either way, it's nice and professional to show it like this with the proton transfer. But if I were grading and you showed this instead, I would also be like, yeah, all right, they're smart. So now, also, if you do show it this way, it's helpful because we still have to keep track of our bromine. And bromine has an important part to play now. We said that our carbocation is an electrophile. Well, bromine has the characteristics of a nucleophile now, right? It's got a 2 load of negative charge on it. It's going to want to find some positive charge. and it's got lone pairs galore. It's got lone pairs all over that crazy cell. So it will behave like a nucleophile. Our nucleophile attacks our electrophile. Our arrow fires off towards that electrophile. And you know what? I went over this in class earlier. I think the better way is to show it directly going into that positively charged carbon. So our bromine attacks this positively charged carbocation. It's really easy to do so because the carbocation is flat. You can see a diagram of this on page 412 of your text. To be an artist right now would be fantastic. But the result of this is we form a bond between bromine and this carbon. And that satisfies that carbon's positive charge. And everyone's a happy camper. Yay!
So
Yes.
Oh, sorry.
That's okay.
Kyle, you're second.
Okay, that's fine.
So in class, like Dr. Hill draws it from like the negative charge to the positive charge, like directly to the positive charge. Is that okay, or like should we draw it like this?
If he's doing it that way, that's fine. I would normally say that's fine. I frequently omit lone pairs because
Yeah, just
I'm
like,
lazy,
he's
but
been like doing it directly from the negative charge.
That's fine.
yeah, if you drew it that way, it would be understood. I think if you also show the lone pairs going to the actual atom that has the charge, that is also correct.
Okay.
And I think that's actually a better description
Mhm.
because showing the lone pairs.
Does it matter if the BR is placed up or to the side?
In this molecule, it does not. And that's actually illustrated on page 412. Because our carbocation is flat, we can attack it. It's not chiral, like a hand. We can attack it from the top or the bottom. So if we attack it from the top, we get one enantiomer. If we attack it from the bottom, the other.
It's not stereo.
Exactly. This is a non-stereospecific reaction.
The only way you have stereo reaction is when you have like water in that, or you throw some acid in it, right?
If we threw water into this,
Because then you have a water.
Hydration reaction.
Well, yeah.
this
but
would no. You're thinking of the you're thinking of halohydrins, but that's with BR2.
Yeah.
Whenever, pretty much
Correct.
any time we have a carbocation intermediate, we're not going to have a stereospecific reaction. Carbocations ruin stereospecificity. All right, cool. So that is our basic halogenation. And we can do this reaction with HBr, we can use HCl, or we can use HI.
Do the same thing.
Yep, same process, just different halogen.
Right.
Okay.
Different halogen. Oh, Kyle, you had a question. I'm sorry.
No, I was about to ask about where the bromine goes.
Oh, where that bromine goes. Yeah.
Yeah, doesn't matter. Like that
It does not matter here because of this carbocation intermediate. Are there any other questions on this one before we talk about the
BR2.
yeah, the BR2 halogenation? This is a hydrohalogenation, yeah, and the other one is just a halogenation.
Number one on the wheel.
Huh? It's number one on the wheel or
That was
what?
number 2 on the wheel.
But it's his favorite.
It's his fave.
If this is not there tomorrow,
This is definitely on
I'm
there.
so
I-
mad if it's on
I'm gonna
there.
draw it on the back just for kicks.
yeah.
I know.
I think also since he likes this one so much, it's good to know the. So this is a Markovnikov edition, right? Because we added onto the more substituted position. It's worth knowing the.
Wait, the HBR one that you showed us? Oh wait, yeah, that is. Sorry, I was looking at the intro thing.
I mean, you gotta know the names for them too.
I wouldn't.
No,
Worry about the
like,
names.
He never like.
Yeah, I don't
placed
really
an
know the
emphasis
name. I just know
on
how to do
names
the
in
damn
this
thing.
unit.
Yeah, I wouldn't sweat names.
Yeah.
He doesn't.
Fridge. Okay. So just real quick,
Yeah, I would do it.
looking at that one again, if we used
BR2.
HBr and we also chucked in peroxides, so either H2O2 or you could write ROOR. It's frequently written that way. This is going to give us the anti-Markovnikov addition. So this is going to generate, break our double bond, and we're going to put our bromine on our less substituted carbon this time. And the reason this happens is because we proceed through a radical intermediate. I'm not going to draw the whole mechanism out, but we have a radical intermediate, and when we're making our radical, we can either put the radical charge on this carbon or on this carbon. Oop.
Wait, what did you say that was called again?
This reaction,
Yeah. What was
this
it?
is just a radical halogenation, I think.
Okay.
It's number 2.
I believe, yeah, we just call this a radical
So
halogenation.
it's the opposite of what you, well.
Yes,
the
because it
placement.
gives us the
They just call it hydrogen.
It's like 9.3.
anti-Markovnikov.
Okay.
And so the reason it does so is because we have this intermediate, our first step is the bromine. One of our first steps in this is a bromine radical attacking our double bond. And we generate a radical on this. So we can either form this species as an intermediate or this species. And we favor this one, which corresponds to our product. And that's because we have our radical is, the radicals are similar to carbocations. They want to be more substituted. And this is a tertiary radical. The carbon that holds the radical has 1, 2, 3 carbon substituents. One sec. And this one is secondary. I didn't draw on that hydrogen, but it has 1, 2 carbon substituents. So carbocations, radicals, double bonds all want to be as substituted as possible for purposes of stability. Yes?
Can you explain your arrows?
Yeah, so this is a radical reaction. We have half-headed arrows instead of the regular old arrows. So when we're moving radicals, normally we use these double-headed arrows. When we move a radical, we use an arrow with half a head because it's a single electron moving, as opposed to 2 electrons moving. Normally, like a lone pair moves as 1 pair of electrons. That's where we get the double-headed arrow. For a single electron moving, a radical, 1 head. And so to break down what happened there, the peroxides react with the HBr to generate a Br radical. And can I use the same substrate? That would be great. So this spies our double bond. It comes at it with one of its electrons. The double bond's like, yeah, I'll let you be a part of my team. One of our double bond electrons goes to meet up with that, and that forms our carbon-bromine bond. The other electron from our double bond, because every bond is 2 electrons being shared, right? The other electron goes and parks itself on this carbon, which generates that radical intermediate I had just drawn. So radical reactions are a little bit more complicated because we generally just have more arrows flying around, which is fun and terrible. Yes?
So, I know it's HBr, but why can't we just like do the same thing we did in the last reaction and just move where the arrows go? Is that not okay? Or
Sorry.
do you get what I'm saying? Like how we put the H where the Br is, right? Why can't we just say that the H goes in the other spot?
Like,
I don't know how to like, describe it to you.
do you want to come up and draw?
Yeah, like
Yeah.
let me show you.
Yes, please. Por favor.
Just because
Yeah.
like we didn't learn like the half arrows in class.
Yeah, he didn't really spend a lot of time on them, which is part of the reason why I don't think this is really something we need to emphasize.
In the solution manual, it shows the way like that you want to show where it just.
Do you know what
puts
I'm
the
saying?
plus.
Like with
Yeah.
like yeah, it's like so we do like the same reaction like the double bond goes to the H and then to the Br.
Oh.
Do you know what I'm saying? Like
Yeah, so it just shows it going down like,
yeah, it to the H and then to the Br and then the only thing that would change is where the H was placed. That's it.
Yeah. That's the
I feel like he did that like that.
That's what he did in class too.
Yeah. That's
So
how
he
it
didn't
is in
teach
the
us like the
solution manual.
radical
But isn't
thing.
that like kind of incorrect?
but
Yeah, that's completely wrong.
That's not favorable in
That's-
a reaction.
That's completely
That's in the
wrong.
But like
book
that's what he's
too.
been teaching us.
There's
Are you
no way you
sure
can
this
make
was
that.
not
That's a
a
minor
counter
product.
example, or
There's
that's
no
wrong?
way.
I'm
That's
pretty sure in the
wrong.
solution manual,
You
that's
That's-
cannot make that a reaction.
That's wrong.
So like what should we do then for an exam?
Because we
Like,
never really
What do you
learned like
do
half-headed.
the right way?
I like that answer. Yeah, do it the right way. So let's just blaze through this mechanism really quickly. Actually, it's in the text, but So this is the main portion of it. We generate. I'll draw this one more time. Our this radical intermediate, and then this ideally finds itself a lovely hydrogen radical.
Wait, how do we get the radical intermediate though?
Okay. All right. Let's go to the beginning. Let's go to the beginning. There's no time for frigging around with this. We just got to do it right. So in the beginning, in the very, very beginning, we have our peroxide. And the peroxides are in here to help us generate radical species. They're not actually going to do any chemistry on our substrate. They're just going to help us get this bromine ready to react. So our peroxides very readily undergo a homolytic cleavage. Our bond breaks evenly to both sides. Homolytic cleavage. And so this is going to give us, technically, 2 hydroxyl radicals, OH dots. So one of these bad mamma jammas is going to come across an HBr, and it's going to be like, oh, hey, I would really like that hydrogen. That'll make me a nice, happy water molecule. Can I have that? Great, I'm going to take that. And so it's like, I'll contribute 1 electron, but you're going to have to give me the other one. And so hydrogen's like, all right, yeah, I'll go over there. And so this is going to generate, so we have 2 electrons coming together. That's going to make a nice OH bond. And the other electron from our HBr bond goes on to our Br. This is going to give us some nice water and a bromine radical. So now our bromine radical is ready to attack a double bond. So we use this substrate still. Br dot is going to come in. The double bond is going to kick out an electron, and the other one will reside to give us the more stable, it will travel to this carbon to give the more stable radical intermediate. So this produces a broken double bond, our Br in the less substituted position, and a radical in the more substituted position. And so the way Dr. Dudai demonstrated this reaction finishing in class was he just showed a hydrogen radical hooking up with this carbon radical. That's not technically correct. It's like kind of correct. That's one way it could end. But you know what? That's what he showed. That'll do. Normally, I would show what we consider to be a continued propagation. This would attack another HBr, which would make another, which would give us our product, Br, and another Br radical, which keeps the reaction going. So the peroxides we had in the beginning are just a little catalyst to get this reaction running. Once it's going, it will just propagate itself. This is normally referred to as propagation. Oh, I'm really making a nice cluster of words up in here. So this is our propagation. Radical.
Is that like the demarcation of radicals, like a little dot? Like it's not like
Yes.
a plus charge?
Not a plus charge, yes. So radicals are non-charged species, generally. Always? Non-charged species, yeah, and they have unpaired electrons.
What's the final product on that?
So let me draw it a little more crisp. It's this dude, and we're just going to grab a hydrogen onto this radical position. So we have our bromine, and yep, we just get rid of the radical.
Do you have to show that beginning part if he gives like a problem like that? Can you just skip to the what you have drawn?
I would show that for completeness,
Oh, really?
but yeah, I would show it for completeness. If you don't remember it, it's not the key part of the reaction, so don't beat yourself up. Don't beat yourself up anyway. It's generally really worth it. So yeah, and the other reaction that I think he was like, definitely know this, is the dope one. I didn't even get to talk about it yet. I was really excited because it's got that bromohydrin, and I love the bros. Bros, hydrins, burp. Let's not make you. Let's just make you look a little different. Let's draw you a little different. Yeah, we'll just do it on a pentene. So if we throw some Br2 at this, this is going to give us trans addition. So these bromines are going to be on opposite sides. Let's put another substituent there. It's going to give us a trans addition. That's really the main thing I think that's noteworthy about this. Let's get the arrow out of here. We'll just do the mechanism. Screw it. No, we'll do it. Sorry. So this, adds trans across this double bond. The way I draw the product is I get rid of the double bond, and I keep two things in place, and then I'm just going to put these bromines in nice and trans. So I'll have one popping out at us, one going away from us, the opposite, and I have to put this methyl group in still. So that should be our product, or one of the possible products for this. Really, if you want to draw this, it's perfectly acceptable to show just Br, because we get a mixture of enantiomers. We're not going to make one
So is that a
specific
racemate?
enantiomer. Yes.
Boom.
Bam, exactly. This is going to generate a racemic solution.
Wait, so why are you adding BR2 to it? Why is it just
Equal
being?
chance of-
Oh, shoot, because I'm stupid and I forgot to write in the 2. Thank you.
Like, does it matter
Dumb
if
face
it's
here.
dashed or wedged?
Dumb guy Jones.
Yeah.
Okay, so if we want to do this mechanism, let's start off. Pretty much all of these reactions that we know thus far feature our alkene as the carbocation. And there's, if I'm not mistaken, a real
Wait, I have
great...
a question.
Yes.
If the methyl was a dash or a wedge, would it not be a racemate? Because
Yeah.
the BR would have to be opposite of the dash or the wedge, so they don't interact.
Keep track of all the.
Wait, if the...
If the methyl group in the original was a dash or a wedge, would it not be a racemate?
Well, it couldn't be, because it's part of a double bond. We never got those dashes or wedges with the double bonds. Everything's nice and plain around those.
What is the rest? Yeah.
So, yeah. Wait, a racemate, if I don't want to say the wrong word. We got racemic mixtures.
50%, 50% is polar plain light inactive. It's optical.
Yeah, we didn't really learn
It didn't go over, but he talked
He
about
named it,
briefly.
he talked about it.
Yeah, he talked about
Yeah.
polarized light.
Is a racemate the mixture itself or the molecule? Do we say a racemate? I'm just trying to remember.
It was in the book.
I'm fairly certain when we say racemate, we are referring to one molecule and comparing it to another. Racemate.
It was in a
Not defined in here. Just racemic mixture.
Oh,
Mother fudger, not in the appendix. Yeah, so I'm going to say it wrong. If somebody wants to Google it, that'd be rad. But I can say that a racemic mixture is where we have an equal amount of one enantiomer as we do the other. And so this reaction will give us a racemic mixture. It will not be what we call enantioselective. We won't form one enantiomer. Yeah?
Just have a question. So, obviously, like on our little sheet thing, it says we have to draw both, like the enantiomers. Should we do that on the exam as well, or can we draw it how you did, like that structure up there?
I mean, if it's on the sheet that has both enantiomers,
So we should just draw both enantiomers then.
yeah, you're probably safest drawing both enantiomers, which is easy. You just
Yeah, just switch.
swap your chiral centers. So
Okay.
we'd have, this BRF and swap those. All right, so let's do the mechanism real quick. We know that the alkene, the double bond, can be a good nucleophile. So there's a good chance this will behave as our nucleophile. And BR, this is a nonpolar molecule because it's bromine pulling on bromine, same electronegativity. It's got a lot of lone pairs, so we might want to say that it is a potential nucleophile. But in this case, it will behave as an electrophile. And we have this really rad, come on, where's the diagram? There it is. It's on page 436. We have a lovely diagram that shows as we bring this negative charge of the double bond near the bromine, it induces polarization. So as negative charge comes close to here, it pushes the negative charge in our bromine to the far bromine atom and leaves this one positively charged. So it comes in, and the electrons in the bromine are like, run away from the negative charge, because like repels like. High-pitched voice. So now that when this comes in close, it induces polarization, and it makes this bromine a pretty dope electrophile. It's got a nice partial positive charge on it. And the bromine-bromine bond is not particularly strong, so it's relatively easy for us to attack this bromine with our alkene. And just like we saw in the addition of hydrogen bromide, when we form a bond to bromine or hydrogen, they like to only have one bond. So their existing bond will break. This does not generate a carbocation, though, like we did before. We get something way cooler. How am I going to draw you? I'm going to draw you like this. So we get our dope bromonium ion, which is a 3-membered ring. And I'm going to show this ethyl group popping up. So we generate, yes, it's this real cool 3-membered ring bromonium ion. And we also have a Br- in the mix. Bromonium ion. So now, what do we have? Yes?
Can you just explain real quick how you drew that, like why you drew that certain structure?
Yes. So the important thing is for the bromonium ion that we form this 3-membered ring intermediate. So there's a variety of different ways I could have drawn this, but the real nitty-gritty way to do it would have just been to show that these two carbons are forming a bond. It's really partial bonds, so if I were really being fancy, I might show them as kind of dashed partial bonds, but I'm just going to show them as lines for starters.
And it's shown like that because it's above the carbon-carbon bond, right?
Or it sits on it.
Yeah, that's right. I think that's what he said in class. That's why
That's
I'm
what
just.
Charles said in lab.
That's why I'm just
Yes, that's
confused.
what
Like
he
I had a hard
said.
time understanding why he was doing it like that. Because then he kept saying it sits on top. Well, I was like, I don't understand.
But like, why does it sit on top? Why
Yeah.
does it make
Yeah.
a carbocation?
Exactly.
Okay, let
I
me
think
draw.
that's
I'm
the
going to do a drawing that the book does. They show it so nice. So if we have our double bond on, this is a cyclohexane, cyclopentene, and we're looking at it from the front. So this is up in the front. Our p orbitals are up and down like this. When a Br2 floats in near this, so this bromine is above this ring that I've drawn.
Okay.
This ring, imagine it as just popping out of the board, nice and flat. So these p orbitals are up, they have electrons in them. Oh, lots of electrons. The bromine comes in, it feels these electrons, it feels the force from them, that negative force, and pushes electron density onto the far bromine and gives this one positive charge. And that makes it a nice situation for these electrons to attack here. So this generates, continuing with this kind of flatland drawing, our double bond is broken, and now we have this. How do you draw a book so it looks pretty? You made it different. Okay. You made it not heinous like mine. This gives us this. This is another way of drawing the bromonium intermediate.
And that's because the orbitals are attracting him.
Yes.
And that's why I drew it like that.
Yes.
Sort of, right?
Yes, that's why I drew it like
That's how
this.
I would just think of it, just simple, just to understand it.
Yeah, so it's being attacked by the electrons in those orbitals, and the carbons are both sharing the bond to it.
Okay.
Cool?
Yeah.
Okay. And I simply drew it this way. it wasn't super simple. But basically, whenever I draw my bromonium intermediates, I don't do it like this. I usually pretend that in the nice flat plane world that is the board, I pretend this bromine was behind our double bond. So if the double bond guy was up here, the bromine was behind it. And that's why I have my bromonium intermediate with the bromine pointed into the back position with these dashed lines. And I just usually keep the trans substituents in the same position. So I draw them the way they were before. Actually, no, this time, no, I keep the cis ones in the same position. That's right. So these two substituents were cis.
And what's the wedge?
The wedge means that it's pointing out. That is this carbon and this carbon.
Oh, that end, okay.
Yeah, that's what's going on there.
Okay.
So why do you keep the cis the same?
That's just how I do it for drawing.
Okay.
And I think that's technically correct. If we imagine this bromine coming in from the back, it kind of docks in and pushes this one forward. Yeah, there's a few ways we could draw it technically. But I like to do it that way. That's just my personal system. I find it works out well. 90% of the time. So, all right, now we've got this bromonium ion. Do you guys think bromonium ion is going to be a nucleophile or electrophile?
That one?
This bromonium
That's going to
ion.
be electrophile.
Electrophile, right? I hear a lot of electrophiles. That's a good guess. There's positive charge on this. Yeah, that's really just our best bet. There's positive charge. And we also have a bromine, and the bromine has positive charge on it, which means it's going to be extra hungry for electrons, right? And we already know bromine has a pretty high electronegativity. It's hungry for electrons. So if it's extra hungry for electrons, that's really going to be pulling electrons off of these carbons. That's going to make those carbons themselves pretty good electrophiles. So the bromine, not a great electrophile itself, not this atom. The carbons it's attached to, though, are very good. And we really want to break open this three-membered ring intermediate because three-membered rings are just kind of pissed off. It's a really bad set of bond angles. Our bonds want to be at around 109.5 or greater. And this is a frickin' 60-degree angle. That's like half of what we want. No bueno. So this is a good electrophile. Our Br minus is a good nucleophile, like we had in the last reaction. It's got negative charge and lone pairs galore. And so it's going to attack our bromonium ion. It's going to attack one of these carbons that will have a partial, I suck at deltas, partial positive charge. Does anybody know which one it will attack?
It's going to attack, in this case, the outside one.
I heard the closest one.
Yeah.
The less stable
one? They're of, I guess you could say, equal stability. It's going to attack the less sterically hindered position. And by that, I mean it's going to come in the easiest route, the route that is least blocked up by other atoms. Yes, on this closest one. And this one has the least substituent, so I guess it's attacking the less substituted carbon. This carbon has a CH3 here, and just a little hydrogen poking out up there. Comparing that to what's on this side, it's going to be much harder for this large bromine atom to come in and interact with this carbon. Because instead of a hydrogen that it has to dodge around, it'll have to dodge a big-ass ethyl group, which is carbon with a crap load of hydrogens on it. So this group is much larger than this little hydrogen, making it much easier for the bromine to attack here, as opposed to this position.
Do you need that wedge line there for the ethyl group, or
On this hydrogen?
no, on the ethyl group?
Yes.
Okay.
Yes, that should be included. So we're going to show our bromine attacking this carbon, and we have to show something else here. Does anybody know what we have to show?
Oh, you have to show the bond breaking between bromine so it gets the electron back. That dotted line.
This wedge line has to break.
Yeah.
And there's a few reasons for that. The most obvious one is we're making a new bond to this carbon, and it already had 4 bonds on it. We can't have a 5-bonded carbon. We're going to have to break one of those suckers off. And the most logical choice here is the easiest bond to break. We already said that this 3-membered ring is very strained and unhappy, so it'll be totally stoked to break that bond. The electrons move back onto the positively charged bromine. So we end up with this structure. We still have a Br here, this on the wedge, methyl group down. And on this carbon, our bromine that came in is now going to be on the top of the molecule because it came in up top and dodged around that hydrogen. So we'll have bromine up top. And we push our, don't goop this up like a goop, push our hydrogen down. And now we have our CH3 here. Cool. Cool.
You have to show the hydrogen?
No, you don't. I just like to put it in.
Oh, no, I just
Yeah. Yes?
How do you know the bromine has to come out, like, on the wedge?
So that would be really wonderful to explain if we had gone over chapter 7, which discusses SN2 chemistry, because this attack, this step here, is an SN2 substitution, essentially, within this other reaction. And so whenever we have, this means nothing, I'm sure, right now, but anytime we have SN2 substitutions, we invert our stereochemistry. That also doesn't mean much without the explanation. I think the simplest way to explain it for our purposes is because this bromine attacks on this top side, because the bottom is blocked up by the bromine. The sides are blocked up by the CH3. It's easiest for comment to come in up top, opposite where this is now.
What's the name of this type of addition reaction?
This is just a bromination.
It's called a bromination.
I think it's just a bromination, right? Halogenation. I guess, okay, it's just a halogenation. But this would be a bromination. Yeah, so these are halogenation reactions. And we can do this with Br2. We can also do it with Cl2. Those are the only two halogens this works with. It does not work with any of the other ones.
Can you show like this?
Yeah, that probably is good too. Yeah,
That's what I'm doing.
I think that's fine.
All right.
Cool. Cool. We can do a fun variation on this reaction. If we add water into this mix, so if we use Br2 and we also put some water in here, we will still generate this halohydrin. I'm sorry, not halohydrin. We will generate a halohydrin. That's going to be our product. But our first step is going to be the same. We'll still generate this bromonium ion. But our second step will be a little different. It's actually not going to be very much different. Instead of using the Br minus, we're going to use H2O as our nucleophile. And so now water will come in. We usually have water as our solvent, so there's a lot more water than there is bromine. And that's why it's easy for this water molecule to compete with the bromine. It's not as good of a nucleophile as Br minus, but since there is assumed to be a lot of it, since it's our solvent, it's like, you know, I don't have a good metaphor. There's way more of it, even though it's not as good, it's still going to win out. So this will do our nucleophilic attack. We'll still have this ring breaking. But instead, this will generate this dude, this intermediate, and then we'll have one more step where another water molecule comes in to help out. Does one deprotonation step to give us a nice happy product of loop, loop, loo-doo-doop, loop, loop, skoo-doo, Br and OH. Get out of here, confusing extra drawing. So, yes, if we add in water into this mix, instead of adding two bromines, we will add a bromine into the more substituted position on the double bond, and we will add in an OH onto the less substitution in the double, less substituted position in the double bond. So this is it's pretty much the same mechanism you guys saw. I only had to change two things, really, and add this extra step, which was, I guess that's the second thing. I just put in OH water instead of Br minus, and I added this last step where we took a hydrogen off of that water who attacked. A lot of people ask about this, and they're like, hey, where did this second water molecule come from? With the WTF, what's up with that? If we said we started out with, just our alkene Br2 and H2O, well then, yeah, where did this crap come from? Since we're,
Unlimited water molecule.
we have, yeah, that's right. We have unlimited water molecules. Since we're assuming that water is our solvent, we have unlimited water molecules that we can use for our mechanism. Most of them are just going to, most of the time when we have unlimited solvent, it's just going to be helping us with proton transfers, like we had here. We had a protonated heteroatom. O is a heteroatom. Very frequently we'll have solvent molecules helping us protonate or deprotonate heteroatoms in our reactions.
You can write that as OH coming out towards you and switch the other two, right?
Yeah, we can totally, we can
Cool.
swap this center and that one to get the other possible product.
Cool.
What did you say the intermediate was?
The bromonium intermediate.
Oh, okay.
So we still have this bromonium intermediate.
So instead of the bromide, you use the water.
That's right. Because we have a crap load of water.
And would that also come into the less hindered position?
Exactly. It would also attack in the less hindered position because it's easiest.
And you know how you drew the bromonium ion with the wedge and the line going across? For the other one, you know how you drew it up for the second part? See the bromonium?
Up there?
No. See the bromonium? Okay, I'll go to the right. This one, yeah, okay. See how you have the wedge on the left?
Yes.
On the left.
On the left. Sorry.
Yeah, and you have the other part of the carbon like going upward.
Oh, that's...
It doesn't matter.
Yeah, it doesn't matter.
Okay, all right. I was just wondering if like placement wise.
No, yeah, that's a good question. But yeah, inconsequential.
All right.
I could just easily
It's
drawn
the
it.
same thing.
Yeah, I could have had it coming down here. Not important, particularly on a non-chiral center. Yeah, we should probably wrap up because I gotta go crush some rocks.
What?
I gotta go climb some plastic rocks at a gym. But if you guys want to get my email and see the notes that I've typed up using ChemDraw, please send me an email. I will try and get those to you this evening before midnight. And I also post this video, which you've already seen. Yeah. Okay. Oh, and they want to know what your product is. So where's our carbocation? Right.
Then there's fucking things with tone and stuff.
Yeah, so we have a secondary carbocation
Right.
next to this quaternary carbon.
Right.
Any idea? There's a sneaky thing that's going to happen here.
This it's gonna do an invert, like this carbon wants this, so it's gonna form into a ring or some shit.
I don't think we have a ring.
That's what it's
Do they have a ring opening here?
I'm probably going to study more. I don't know if I'm going to go to the tech or if I'm going to go home.
To form the six-membered ring? All right, yeah, so it is ring opening. My first thought looking at this was that we would have just a
Yeah, what ship? That's right.
a methyl ship.
So yeah, I'm gonna study chapter 2.
So the reason I feel like I know everything else, but theoretically give us this.
And this is the most stable now. It's gonna keep going back and forth, so you gotta do it right.
Right. I see.
Funniest thing I've seen in the book was the trains.
So, and that's why we have the ring
Yeah, the
opening.
train 7-member ring.
Ring opening
I haven't
sucks.
seen it.
All right, yeah, so since we're going to
No, it
a
was
5,
crazy.
that just only works because we're going from a 5-membered ring to a 6-membered ring. We'll never open up a 6-membered ring into like a 7 or make a 6 into a 5.
Right, so how do you,
I'm going to turn off this video.
DJ, is that
Oh,
really
yeah.
where it's open?
yeah.